Hi, welcome to the Signal Path. In this episode, we're going to take a look at the JouleScope JS220, which is a successor on the 100 series that's been on the market for some time, and it has some improvements and enhancements that I'd like to talk about. This is a precision energy analyzer. Essentially, it's a digitizer that digitizes current and voltage across a particular device, and it can give you all kind of information about its energy consumption across time and various dynamic behaviors it has. Now, this particular model has 6 orders of magnitude dynamic range on the current measurement with some clever switching, which we will take a look at once we open it up. Now, it does have a front panel PCB that is actually removable, and it connects to the internal one. We'll see it when we take it apart. And it can measure voltages plus or minus 15, current plus or minus 3 amps with 10 amps of peak current, pulse current. It can't really sustain 10 amp for a long time. So it really measures a 4-quadrant current and voltage, which is quite nice. So you can see batteries charging and discharging, for example. It does have some IOs. It runs from USB-C, and it does have a trigger for synchronizing it with other external instruments. Now, there's a lot we can do with this, but I'm really interested in pushing it into some of its corners where it may not be so comfortable operating and checking to see how it works and how it does switching between its 6 order of magnitude of current measurement. So first thing first, let's take it apart and understand its architecture. So I have the photo of the board here. There's really not much on the other side. There's just a few decoupling capacitors underneath these big BGA devices. And on the right side, we have the X-ray that I just took, and it's nice to see them side by side because the X-ray gives us a little more insight into some of the design decisions that have been made on the board. Now, the fundamental principle operation of something like this is really quite straightforward. You just have to digitize 2 channels. You have an ADC that digitizes the voltage, and you have an ADC that digitizes the current. The current is digitized by passing it over a known value resistor and then amplifying that voltage, and then of course digitizing that. Now, even though fundamentally this is a simple concept, there are a lot of design decisions that has to go into this and a lot of subtlety into how you do this. Now, everything on this board needs to be powered with the USB-C connector here on the right side. But at the same time, we need to fully isolate the device under test from all the human interface components like the USB-C trigger and the digital I/O. And this is a classic technique. It's done for multiple reasons, primarily for the protection of the user and the devices from the user itself. Now, the device under test that you're measuring is not powered from the instrument at all. It only measures it, simple as that. So this is not a power supply for that. But if you look on the X-ray on the right side, you can clearly see the cutout in the board. And that is fully isolating everything. Now, you still need to get signals across, which is done, of course, with opto-isolators. So if you zoom in here, you can see an opto-isolator here that has multiple channels, and those very faint lines you see in the middle are probably a way to guide the light so that they don't interact with each other. This is a multi-channel I/O. There's also a fast version of it up here. This is a much faster I/O, probably for some really rapid signals that you need to get across. The rest can be for configuration. If you go down, you can see the cutout very clearly. There's another cut over here, and this part is connected through here, and that's the last bit of the I/O. You can see the multiple channels through the X-ray passing through. Now, this is good for sending I/O, but it's not really good for sending data. Well, technically speaking, you can send power using optical methods too. I'm actually working on a review of something that does exactly that, but in this situation, it's just not worth it. Instead, they're using a transformer, which is basically a DC-DC converter configuration. You just modulate current on this side, and you pick it up and rectify it on the other side. If you go ahead and look at what that looks like on this side, you can see we have 2 bridge rectifiers, full bridge rectifiers on this side connected to the various transformer ports, and that creates DC voltages, which are then handled on this side and create multiple power supplies. So all of this at the top and all of this stuff over here is just purely for power supplies. This Atmel over here controls the USB-C interface and a bunch of other things to do the DC-DC conversion stuff working. Now, on the other side, we have a lattice FPGA or a CPLD on this side, which needs to be there in order to capture, communicate, configure, and basically handle everything that happens on this side as fast as possible. And we will get to why that is so important. Now, at the heart of the digitization on the left side, we have 2 ADCs. These are analog devices, and these are ADS 9226, I believe. These are 16-bit 2-channel 2 megasymbol per second or 2 megasample per second ADCs. And this instrument doesn't behave like a regular oscilloscope, but you have a trigger and then you have a buffer and then you need to rearm it. It's a continuously streaming device, which has major advantages because there's no gaps in its storage. You just basically send everything through the USB-C, let the host computer deal with it afterwards. But it needs to be conditioned and calibrated, and all of that is done through the FPGA over here before the data is reconfigured and sent back to the USB-C. So it's a nice architecture from that point of view. Now, if you look at these ADCs, they're actually dual channel as far as I could tell. But how are they managing to do the current? Now, this is where all the magic of the current measurement is. So in order to measure the current across 6 orders of magnitude, you basically need 6 individual resistors, or at least you could do it with 6 in order to get a really good result. And these, I believe, vary from 0.11 ohms all the way to over 1 kilo ohm. So we have 1, 2, 3, 4, 5, 6. And these MOSFETs over here switch these resistors in and out depending on how much current is coming. So let's say you're measuring 1 amp, okay, and you're on the highest setting. When you jump from 1 amp to 1 microamp, you need to step all the way down to the smaller resistors in order to maintain a reasonably small voltage across these resistors. Otherwise, you're going to have either a very, very large burden voltage or way too small, such that the ADC can't get any reasonable measurement. And I think what they're doing is that they're looking at more than just one resistor at a time in order to minimize the overlap of the switching so that they can de-embed that. So imagine that one of these resistors is always on and it's always monitoring, and there's some dedicated hardware associated with that. So when you hit the point when you need to switch from one resistor to another resistor, you now have that overlapping region. You can use that in your software to correct for things and to make sure you don't miss any transient effect between them. I believe this instrument can do a 1 microsecond smaller step between those two adjacent switches, and that's pretty impressive, and that's one of the key differentiating features of this. Now the current measurement over here is amplified with various op amps. You can see one over here, and I think it looks at 2 channels at the same time. There's also another TI component here. You can see that there's some traces going onto this one, and there's some voltage traces going here. So this is probably measuring for voltages, and these are the current traces going into these MOSFETs and then switching in and out. So I think that's the trick here, that they're using multiple channels of these ADCs at the same time, looking at overlapping resistor values to do this fast switching and de-embedding so you don't miss anything, which is clever in its design. And there's also some level converters over here. There's some memory which loads into the lattice when it powers on. The rest is really nothing unusual. It's just some good analog design and some clever switching for the 6 orders of magnitude of the switching of the current measurement. And on this side, you can see a better look on the X-ray. It's cool to see the connectors and how they hug the pin that goes on the inside. These 2 holes are for where the optical or the light pipe is connected. You can see that's the light pipe showing what is going on with the instrument state. There's also another big cut here in the PCB. This is probably done to reduce the voltage coupling and any noise coupling from this side where the FPGA is to the other side. That it ends over here, probably as high as they could go. You can see some traces wrapped right around this to get across. It's nice. I think it's a nice design. It's very compact. It's difficult to do this in such a small area and not have a whole bunch of components on the other side. But the fundamental principle of operation, again, is pretty straightforward. I do like the switching here that's done on these, and we're going to have to measure it and see how it performs in real life. Let's do a quick measurement to verify the internal impedance used to measure current using the JouleScope. So I have a banana connector over here. You can see I am doing a 4-wire measurement. So the measurement plane is actually right over here, which means the entire impedance through here and back on the current measurement is being measured using this setup. Now keep in mind that the impedance used to measure the current directly is in series with all the traces. Now the traces don't matter so much because the voltage is measured across the resistor, but we would have no choice but to measure those traces at the same time and see the switching a little bit. Here I'm going to use the Keithley 2450 as a source measure unit to measure the resistance. Let's zoom in here and see what happens. So currently I'm pushing 100 milliamp through the instrument, and you can see the calculated resistance is 0.028. Now the actual resistor is supposed to be 0.01, which means the rest is the traces which we cannot get rid of. I can actually force the instrument into a particular current measurement range, which changes those MOSFET switches. Right now we're in the 10 amp range. Now the next range after that is 180 milliamp. And if I switch to 180 milliamp, you can see that we indeed add about a factor of 10 to that resistor. It should be 0.11, is now 0.13. We have the same offset as we had before, so it all lines up quite nicely. Now the next range is 18 milliamp, which is under the 100 milliamp I'm pushing in. So I'm going to change that and actually put 1 milliamp into the instrument. The current shouldn't change so much. There's going to be some inaccuracies because at 1 milliamp it's difficult to measure such a small resistance. So let's switch to 18 milliamp range. You can see it goes up by a factor of 10 one more time. We can now switch to the 1.8 milliamp range. One more time it switches up. And we're going to make that even smaller. Turn this into a 10 microamp current. Shouldn't see too much of a difference again. So now we're going to change that to 180 microamp. Another factor of 10. and then finally 18 microamp, and the last factor of 10. So indeed it does have this logarithmic range. Every time you change by an order of magnitude, the resistance changes by an order of magnitude. Now I haven't shown the GUI yet, I just wanted to verify that this works and it kind of makes sense. Remember, the resistances of the MOSFETs and all of those things are in there, and they can be calibrated out of the instrument afterwards. So let's take a look at the GUI and do some actual measurements with the unit. So first let's use two SMUs, two 2450s from Keithley, to apply current and voltage simultaneously to our instrument and see what it does under those conditions. So something you have to keep in mind is that the voltage measurement of this instrument is completely floating. So there is no reference ground here. So you have to share these two terminals together in order to get a reliable measurement. Otherwise it's very susceptible to picking up interference from the environment. And this is a positive terminal that is shared with the current. It's a current measurement on the high side. So it does and can cause some issues if you have different voltages that you're trying to measure that are independent of each other but cannot be shorted together. Something to keep in mind. But for most IoT applications where the voltage and the current are of the same DUT, this is not a problem. So let's go ahead and make some measurements using the JouleScope multimeter. So I'm applying 5 volts from the SMU and 1 amp at the same time, and you can see these numbers are extremely close. They're essentially exactly what the SMUs are telling me, which is a very good sign. So indeed it does meet its specification at this range. Now we're measuring 5 volt here. Now look what happens if I change the voltage range from 15 volts to 2 volts. Well, it just simply says 2.2, which is the over range of about 10% or so over 2 volts, but it doesn't tell me anywhere, not that I can see, that we are overloading the input, and therefore you could be making an erroneous measurement and never know it. This should be pretty easy to fix in software. Just have a flag that tells the user that, yep, you're overloading. Make sure you adjust your voltage range appropriately. So let's go back to 15 there. So there's 1 ampere being measured. Now our current range is automatic. I'm going to go ahead and try now 100 milliamp. It should change the range into a lower one. Here's 100 milliamp. You should measure it perfectly correctly. There it is, 100 milliamp, no issues at all. And let's try 10 milliamp. Here's 10, also no problems. 1 milliamp, looking good. And here's 100 microamp. We're pushing into the lower ranges now. No problem there neither. Here's 10 microamp. Also pretty good. 1 microamp. We're getting pretty close to the bottom now there. I'm going to try 100 nanoamp. At 100 nanoamp, we're still getting, definitely meeting the specification, and it looks good. And there is also some loss actually in that BNC cable that I have connected. So there's going to be some loss in there, but it looks quite close. Now, if I go to 10 nanoamp, then we start running into some problems. At 10 nanoamp, now we are quite a bit off. So even though the instrument does have a 1.5 nanoamp resolution, the accuracy is not quite the same thing. If you look at the datasheet, they do mention that. So here's the resolution at the 18 microamp setting. We're getting a resolution of 1.5 nanoamp. But if you look at the accuracy, it's plus or minus 0.25%, plus or minus 30 nanoamp. So we have about a 40 times the resolution uncertainty in terms of the accuracy of that measurement. There's also similarly what's mentioned for the voltage. So yes, you might be able to see differences or steps that are pretty small, but don't count on making absolute measurements down in the nanoamp. Is not going to be able to give that to you with any reliability there. So, but overall, it's quite good considering what we're doing with it, and considering the fact that it is using a data converter and sampling at 2 megasymbols per second. I think it's quite nice. Now, one other thing is that let's go back to 1 ampere. Okay, so let's push 1 amp in it. Now, if I go ahead and change the range manually from auto and I put it into 18 microamp, it shouldn't get damaged. There you go. But of course it makes the incorrect measurement now, and it doesn't tell me that it's making an incorrect measurement, but it seems to survive. Depends on how much voltage you put across those terminals. I haven't tried to damage it, but of course that resistor that you saw during the teardown could eventually at some point be damaged. I don't know if there's enough protection built into that to automatically disconnect it, but I think that can also be easily done in software. If I go back to the 10 amp measurement, you can see we get our measurement back perfectly fine. If I put it into auto, we also perfectly fine. So yeah, overall looks good. Just a few tweaks to the software would certainly remove some of these doubts and confusions that may arise. So here's our setup to take a look at the dynamic behavior of the JouleScope. There's a couple of things going on here. Let me explain this to you. So this is our load, and this load is nothing more than a MOSFET and a power resistor. We can control the gate voltage of the MOSFET, which changes the amount of current that goes through the power resistor. Now, because we can control the gate voltage, we can completely shut down the MOSFET, which brings the current essentially down to zero. Or we can crank it up and get amps of current, which means that we can take the JouleScope through 6 orders of magnitude of current very quickly across any shape that we want, any kind of waveform that we want. So that's how this is set up. The JouleScope measures the current through the load. At the same time, it measures the voltage that is across that load. And then I also have the Tektronix 2 series here. I'm actually only using it as an arbitrary waveform generator. So it's generating an arbitrary waveform which is connected to the gate of the MOSFET over here. And then I have the Keysight DSOX3104T, which is connected to a current probe. And this allows us to measure the current using a different instrument and to make sure that current is continuous and there are no glitches in it as the JouleScope goes through its many dynamic range switching for all of these various loads that it has. So this combination is going to allow us to now do some precise measurement on this instrument. And here's the scope view for the JouleScope. And currently we're plotting 3 things. We're looking at the current range, and the voltage. The current range is the configuration of the MOSFETs that control the resistors on the current sensing path. And right now it's set to 7, and 7 actually represents off, meaning that none of those MOSFETs are turned on. This is a useful feature, and is indicated right over here. You can see that I have completely turned it off. Off means that the current plus and current minus of the instrument are disconnected from each other. This is helpful because it means you can turn off your device under test directly from the JouleScope by essentially breaking the wire. And this is good if you want to turn it on and look at the startup behavior. This is an easy way of capturing that startup behavior directly here in the software. And there are other safety benefits and so on to it that you can use it for. Now the voltage is there. There is some voltage across the load and we're measuring it. It should be about 12 volts and it's very close. The difference here is because of the power supply itself, which is not generating a very accurate 12 volts. It hasn't been calibrated in a long time. So given that this voltage is constant, is what we expect because there's no current flowing, so it's just sitting steady state. Now I can go ahead and enable this, and as soon as I enable this, we will see the waveform through the power resistor because there is already a waveform on the gate voltage of the MOSFET controlling it. But we're not seeing it because everything is disconnected. All right, let's turn it on. Now as soon as I turn it on, we see our waveform. Now the waveform I'm applying to the gate of the device is a sinusoid at 1 Hertz. That pushes the MOSFET to be on and off to take more than 2 amps into the power resistor, as we talked about earlier. And you can see the waveform looks quite nice. Let's take a look at a couple of its features. Now keep in mind that we have a 30-second of buffer that's continuously streamed as I described during the teardown. Now it's nice because there's no triggering required, but at the same time it would be nice to have at least some kind of a software trigger here. Otherwise, when you zoom in a lot, it's just going to move all over the place. It's going to be very difficult to see anything that's changing live like this. I would have liked to see that. But we can pause it, of course, and we can look at it once it's paused. Then you can, go left and right. You can drag the waveform. As you can see, it's reasonably responsive. Zooming in and out is very responsive. So I'm reasonably happy with that. Now, if you look at the waveform of the current, you can see that there is a couple of tens of millivolts of change once we enable everything. And this is due to the IR drop of the cables from the power supply to the power resistor. It's nice that it can be captured. And this is the expected behavior. With a cable that's short, couple of tens of millivolts for when you have 2 amps is expected. So that's nice and it makes sense. Now, if you look at the current range, you can see the current range goes from 0, which basically is the highest amount of current that it can provide, all the way to 5. So all 6 different stages of current control are exercised right now. So we're taking it through all of its dynamic range because of this waveform. And the waveform goes from almost 0 to over 2.2 amps. So let's zoom in a little bit over here. And let's put a marker here and put the marker when it's in the middle. You can see it in the middle. We're talking about currents. How small is that current? It's almost nothing. It's in the hundreds of nanoamp. Now the reason it's in the 100 of nanoamps as opposed to completely 0 is because it's almost impossible to turn that MOSFET completely off. When it has 12 volts across its source and drain, there will always be some leakage. If I zoom in here, you can see the waveform here. It hits a minimum of around this value, about 600 nanoamp. Okay, that's about correct. That still brings us to the lowest current measurement stage. Now when the current is low, as soon as it begins to go up, the instrument has to react, and it has to react by changing those MOSFET switches appropriately. As soon as the current passes about 18 microamp, it needs to switch to the next stage. So let's see how it does that. And take a look at that. First thing it does, it brings the current all the way down to stage 0, and then slowly steps it up as it tries to measure and find out what the nominal value is. Now this is safest because you bring the current to its lowest value, you don't damage anything, and you slowly step it back up. The disadvantage of that is that you're going to spend the longest amount of time with potential inaccuracy in the measurement of your current. But that's okay. I think it's okay to have this. You should be able to change this behavior if you want to. In fact, if you go under the preferences, if you go under the current ranging, there seems to be some control over this, but I played with these values and I could not get it to do anything different. Either I'm doing something wrong or there's some issue with the software that should be addressed. But nonetheless, it does exactly what you would expect. It scales it back down, jumps back up, and it settles to current range 4. Now the next time, when it saturates that layer, you will expect the behavior to be repeated. And in fact, it does it again. Jumps back down. This time it settles in level 3. And it does this over and over again, all the way to when the current is large enough that it essentially only needs to jump down once, and then the current goes to its highest value. And then all the way through this range, it's sitting in a 10 amp range. Once it's over 180 milliamp, it has to sit in this 10 amp range all the way through. Now on the way down, it's a little bit safer because it's going the other way as the current drops down, so it doesn't have that glitch. You can see the glitch over here is quite a bit smaller. Let me zoom in all the way here. If I look over this, I can put 2 markers. One marker here, and one marker here. You can see this duration here is about 22 microsecond, which is perfectly fine. And some of these glitches are just a function of the fact that there will be some inductances and it's going to create a little bit of trouble. But for most things, it probably doesn't matter. It's just important to be wary of it. Either way, it is captured. So if you see it to be a serious problem, you can, of course, go ahead and adjust that. I really like this red lines that it puts on because when it's not visible, the minimum maximum value, it plots it for you. So you know that if you do zoom in, you will see it. This is a clever way of showing hidden features in the waveform that may be otherwise invisible. It's nice. It really does make you not make some mistakes that would otherwise kind of pass your vision. So let's play that again. I'm going to go ahead and increase the frequency. Let's go from 1 hertz to a kilohertz, which is quite a bit higher. Here's 1000. There you go. So the waveform is now much faster, and again, very nice to see. The plus and minus are shown. We have to zoom in a lot more to see the waveform through the aliasing. There we go. Nice. Let's pause that. So now the behavior is a little bit different because the time scale is very different. We're looking at a kilohertz signal, and it does do some funky things trying to figure out what the best place is to put this. But again, it works. Now the waveform doesn't look as nice anymore on the voltage. This is not a fault of the instrument. It's just because at the kilohertz, the inductances on the lines matter a bit more. So you do get some overshoot and undershoot and a little bit of ringing from all the inductances that are around. But it still captures this quite nicely. The glitches are still almost invisible. It looks really good. I have to say that for capturing very quick, brief events, even at massive dynamic range, it does a very good job. And those algorithms, by overlapping the resistors, certainly has something to do with it as well to be able to measure something so subtle here. So let's take a look at the oscilloscope to make sure that this waveform is exactly what is true, because we're measuring it with a different set of instruments too. There should be no glitches in that waveform, just like there are no glitches in this one. Let's take a closer look at our waveform over here. Zoom in a bit more, and you can see that there are indeed no discontinuities at all. This is also what JouleScope tells us. If we span through the waveform, it's perfectly continuous. There are no glitches. So those switching MOSFETs aren't making any difference. Even this little tiny slope is reproduced inside the waveform captured by JouleScope. So this overall gives me a lot more confidence that we're not missing anything, any dynamic behavior in the overall measurement. Now we can create a fairly difficult situation for the JouleScope. This is a 100 Hz square wave now being applied to the gate of the MOSFET. And that's going to make the ranging a lot harder. So let me pause that. We can zoom in and see what it does. So it still manages to go through all the ranges. So as soon as the current drops, it ramps up the range and it reaches the range of 5, which is the smallest value. And then as soon as the current goes up, you can see it has rapidly switching back to range 0 in order to accommodate this. So it still gives us a fairly accurate measurement in between the two stages. So it does go through all the ranges. But if you push the waveform to a higher frequency, we can make its job quite a bit harder. So let's go to 10 kilohertz, which is a lot more challenging. So here's 10 kilohertz. In this situation, if I zoom in, you can see that it has a much harder time. In fact, it has such a hard time that it doesn't have enough time to switch to any of the higher ranges when the current is low. Now, part of it is because of this ringing. This ringing also, in fact, should be captured correctly. So it doesn't really go higher. It could be potentially because of the ringing that it's experiencing here. But we're also pushing the sampling rate. It makes the algorithms a lot harder. If I push that even more and I go to 100 kilohertz, like so, now it really has a hard time. So we can't really fault it for that. It doesn't even change the range anymore. And anyway, in some ways it really shouldn't do it because these currents are still quite a bit high and the samples do not give it enough time to do that. And in some situations you may be able to play with the settings of the auto ranging, although I haven't been able to do that in order to correct for this. So overall, yep, it's going to be able to capture some subtle effects. And if the frequency is very high, well, this would be the wrong tool for it at this point. But overall, I'm happy with it. So let's go ahead and measure an actual IoT device. This is a motion sensor, and this is connected to my Samsung SmartThings hub. Now, every once in a while, it's going to send a Z-Wave packet to it. It's going to update its temperature and its status, and whenever it detects a motion, it's going to send additional packets. Now, normally, this thing is supposed to last a very long time on a single battery, so you expect the communication to be fairly infrequent. And whenever it, of course, detects a motion, it has to send additional messages. So I want to know how much current it burns, how long it takes for it to send its message, and generally how it behaves across time. So let's give it a try. And here we are, we're capturing the current and the voltage again, and we're also this time capturing the power, which is just simply the product of these two. We also are looking at the current range too. So you can see every once in a while, it's going to create some activity and it's sending some packets probably back to the SmartThings hub. And you can see those activities, especially the envelope of them marked by this red peaks here. Let's pause this and go ahead and zoom into one of them and see what it's doing during that time. There you go. So it's clearly sending a very, very big pulse initially of current. It's consuming a lot of power during this short time, probably when the radio is active. Then it settles down, does a bit more computation, and goes back down. Now we can look at how much power it burns during that time. So it goes as high as just over 400 milliwatt of power, but the duration is quite small. So if I measure the duration here, it's not going to be a lot of time. There we go. What are we looking at? We're looking at about 100 microseconds or so. And that's not a very long duration, and it needs that in order to send the packet back. So, of course, it's going to have a long battery life because of this. Now, one of the things you can do is you can let this run for as long as you want, essentially, because it's constantly streaming. And we can go ahead and clear the accumulator here. And right over here, it is going to accumulate how much energy this thing is burning. So you can leave it running for a long time, or you can have it in its natural environment and estimate the battery life based on how much energy it consumes in an average scenario, for example. Now I'm going to induce some motion, just waving my hand on top of it. And there it is. So those motions are going to create additional packets that is going to let the hub know. And we can pause it again and zoom in here and see some of those behaviors. There we go. So there's a big peak again. So it's probably sending some message. It's checking a few things again. And it's going to consume quite a bit of power during this. So if there's a lot of motion in front of it, it's going to run out of battery faster. And that's to be expected, of course. But yeah, so you can see that you can capture these things pretty nicely. And you can also do a couple of other neat things. You can here enable the GPIO. And you can map these GPIOs to the least and most significant bits of the voltage and the current. So you can use it to sync with other instruments. There is a BNC in the front, which is a trigger, so you can use that to sync with other things too. So overall, I think it's both thought out. A few things here and there in the software can be improved, but certainly if you want to measure IoT devices, this should be able to do it. And there you have it. I hope you enjoyed this detailed review of the JouleScope and the experiments we've performed with it. It's going to be useful around the lab for other experiments in the future. There's actually a widget that they have built to show you how it works, and you can connect it to all the terminals and it runs from USB-C. But I didn't want to use that widget because I'm sure that's going to show up in many other videos on the internet. I just wanted to do my own experiments independent of that so we can really push it to different corners and see its behavior. As always, let me know what you think about this in the comment section, and I'll see you there.